Good afternoon, I'm Dr. Swan, and today we're covering Lab 3 with Bio 139 at BCTC. For those of you following along with at home, if you have your pre-lab worksheets, we'll go over this. We won't go over it in direct order, so kind of sit through and follow through in person. And we're going to go through the lab manual parts as well. With this, we have the heart as a pump today. We're going to pump through this and simulate what the heartbeat is like with an abnormal bradycardia style heart rhythm, something that's slower than what's healthy, than a normal heart rate, which is going between 60 and 100 beats per minute. And then we're going to show what happens with tachycardia when your heartbeat is elevated. For our all intents and purposes, tachycardia, we're going above 160. So that's above your normal exercising heartbeat rate. With our model today, we have a homemade heart as a pump model. It's used through 3 different bottles here. This is going to represent the atrium. This one represents the ventricle, and this one represents the body. We'll also be simulating the valves. This is our mitral valve, or our bicuspid valve, and this is our AV valve to show that stopping point where the valve is open and closed as it's pumping. So we'll go through a little bit of basic heart review here. We'll go through a more in-depth review next week, but just so you have a good idea what's going on when we do our experiment today. We have your heart traced out here. There are 4 chambers. The top portion are the atria. The bottom portion are the ventricles. With the heart cycle, you have oxygen poor blood coming in through this right side here. The atrium is sort of that storage. It's like the atrium of a building where it's pouring down. The ventricle is the part pushing out. With the left side, we have the blood going out into the body. So with our model here, we have our mitral valve because we're looking at the left side of the heart. We're not looking so much at the right side of the heart. There are a few different words that you'll have come up on this today too. Some vocabulary, our stroke volume. Our stroke volume can be calculated using our end systolic volume and end diastolic volume. The stroke volume is the blood that's pumped out per cycle. So with every single heartbeat, that's our stroke volume. We'll be calculating some stroke volumes today as well. And then we have our cardiac output. Cardiac output is the blood pumped out per minute. So when we're calculating output, we're taking the stroke volume and we're multiplying that by the beats per minute. With our lower heart rate, we'll have 12 beats per minute, so we're going to multiply by 12. With our regular heart rate, we'll have 60 beats per minute, we're going to multiply that by 60. And with our abnormally high tachycardia heart rate, we have 185 and 190 that we're going to multiply by. This is our heart as a pump. This bottle right here represents our atrium, this bottle represents our ventricle, and this bottle represents our blood. These straws coming through, we have valves that we're going to simulate as blood pumps. This valve right here represents our mitral valve, or the bicuspid valve, so we're on the left side of the heart during this experiment. And this represents our AV valve, or atrioventricular valve. We're going to see how one valve closes when the other one opens during the pumping process. First, we'll go to really slow pace and show how the blood pumps. We'll go through the atrium into the ventricle with our AV valve closed. If the AV valve is open, it won't pump through effectively. When the AV valve opens, the mitral valve will close and our ventricle will pump into the body. If our mitral valve is open, we'll get backflow and it won't go into the body. The AV valve opens, the mitral valve closes, the ventricle contracts again. When we speed up this process, we have a more efficient blood flow going through. A healthy pace would be 60 to 100 beats per minute. If If we start going faster than that, we won't have much blood flowing through at all. This faster pace, our valve's still closed, but we don't have enough time to push over from the atrium to the ventricle. The filling time is decreased and not as much blood will go to the body. This was our heart as a pump. During our exercise, we showed a couple different ways that you'll find through your manual. So first we'll talk about what Protocol 1 covered. Protocol 1 was bradycardia. That's when our heartbeat is slower. In this experiment in your manual, your Protocol 1 bradycardia was 12 beats per minute. That's a very, very slow heart rate. With 12 beats per minute, we have some numbers on trial here. We started off with, in your manual for your heart pump, you'll subtract 4 from your first one. On our first trial, we pumped out 10 milliliters. We already had 4 in our body. So our stroke volume was 10 minus 4 to get 6. We continued through finding our stroke volume. Our next pump, we had 20 milliliters measuring into our body. We took our 20, subtracted our 6, and had 14. We carried this through all the way to the end, finding an average stroke volume of about 9.7 milliliters per pump. We follow this again, and you can see each pump, you don't have the exact same number. The heart pumps out a different amount each time, so we're looking at our averages. We did the same experiment again and found an average of 8.7 as our stroke volume. Our cardiac output was the total amount that went from the ventricle into the body at the end. For our first trial, we had a total amount of 120 milliliters. We subtracted our 4 from the beginning because we already had 4 milliliters in the body, and we ended up with 116 as our cardiac output. So this was the entire amount going through the heart into the body per minute. Our stroke volume was 9.7. That means we had 9.7 milliliters going from the heart into the body per cycle. We took the averages and found an average with the slow bradycardia heartbeat to be 110 as our cardiac output, with a stroke volume average of 9.2. When we repeat the experiment again, using a heart rate of 30 and then multiplying it so that we have 60, we have a completely different outcome with our cardiac output and our stroke volume. This is representing a healthy patient in contrast to our last set, representing a patient with a very slow heartbeat. With our healthy patient on trial 1, their cardiac output is 330 milliliters. Trial 2, their cardiac output is 360 milliliters, giving them an average of 345 milliliters per minute of blood cycling through. Our stroke volume is higher as well. We have a stroke volume of 11 and then 12 with an average of 11.5. This compares to our last patient who had a cardiac output that was below even 200. That healthier heart rhythm allows for proper filling and for time to push it through the whole body. In the next trial numbers, we'll look at a patient with tachycardia, or a patient whose heartbeat is going so fast it can't push the blood out efficiently. Now we compare our 3 different experiments that we did together. First, we look at that bradycardia, that slow heart rhythm. We had 12 beats per minute. Our cardiac output was 110 milliliters per minute, and our stroke volume was 92 milliliters per cycle. Then we increased to a healthy rhythm, where at 60 beats per minute, we had a cardiac output of an averaging 345 milliliters, and a stroke volume of 11.5 milliliters per cycle. When we increased our heart rate to a tachycardia, we had 185 beats per minute. Our cardiac output decreased to 290, and our stroke volume came down to 1.6 milliliters. You can compare these values and see the differences between a healthy heart rate and an unhealthy heart rate. With the slower heart rate, we have a low cardiac output and an almost healthy stroke volume. With this really fast heart rate, we have an almost healthy cardiac output, but a very bad stroke volume. We can look at what these things have in common too. What does heart rate have in common with cardiac output? Well, we can see a healthy heart rate and a fast heart rate will give you a high cardiac output. But what about heart rate and stroke volume? With our heart rate, the stroke volume came down quite a bit with that high heart rate. This has a clinical value when you're looking at hypertension. Your cardiac output can also be increased through an increased preload. That's having enough to pump out. That's where we see a lower cardiac output in the fast versus the healthy. If we don't have enough to push out, if we haven't had that filling time, then we won't have as much to push out. We're also looking at force and contractility. When our heart has more force to push out, when it has that time to contract and force it out, or it's stronger, we'll see an increased cardiac output. Now we'll go through the rest of your pre-lab. So if you're following along at home, you can grab your pre-lab sheets. These are really good to study over for our exam too. With our heart rate, we're looking at things that increase and decrease. So here's some ways that we can increase our heart rate. We have our sympathetic stimulation. Your sympathetic is your fight or flight. That's the bears chasing you through the woods. The heart's going faster. We also have thyroxine. This is a thyroid hormone. With people who have hyperthyroid or overactive thyroid, they produce more thyroxine, and one of the symptoms will be an increased heart rate. It will be a really fast flutter in their chest. Caffeine will also increase your heart rate. For those of you that have drank too much coffee in the morning or in the middle of the day, you might experience a flutter in your chest feeling, or you get that heat that comes through. That's from the increased heart rate. We have a couple things on our pre-lab that also talks about decreasing our heart rate. One way to decrease the heart rate is with calcium ions. That increased calcium absorption will slow down the heart rate and give you stronger contractions. You'll see this in some forms of medications for heart rate. You also have parasympathetic stimulation. Parasympathetic is the opposite of sympathetic. Parasympathetic is rest and digest. This is when you get home, you're calming down, the test is over, you're relaxing. You have that parasympathetic stimulation where your heart slows down. We have 3 different things that affect stroke volume. First, we have your preload. The preload is the volume that's filling the ventricles during diastole. Diastole is when the ventricles are relaxed before the contraction. The more volume you have, the higher your stroke volume because it's more fluid to push out. A lower preload, like when our heart was beating too fast, will decrease your stroke volume. Next, we have contractility. Contractility is the ability to contract. It's that force the heart is going at. In a strong, healthy heart, we'll have a lot of force. We have a lot of contraction. We'll have a high stroke volume. In a weak, slow, healthy heart, you don't have as much contraction because that muscle's not as strong. That contractility, when it contracts well, you'll have a high stroke volume. Our heart rate is the last thing that affects your stroke volume. This is the speed of the contraction. We could see before in our experiment, with a fast heart rate, we weren't getting as high of a stroke volume. That dealt with it going so fast that there wasn't enough in the preload. With a slow heart rate, we still don't have as much stroke volume because we're not using as strong of a contraction. With a healthy heart rate, we have a healthy, good stroke volume. Next, we'll cover positive inotropes and contractility. Inotropes are anything that gives a stronger heartbeat. It's typically a prescription, but there are some different things in your body that can work the same way. We're looking at calcium. Calcium is something that'll give you that really big, strong heartbeat. It'll reduce the heart rate, but it'll cause a stronger heartbeat. We have beta blockers. Beta blockers slow down the heartbeat and they make a stronger contraction. Angiotensin II, this is something that we'll go more into detail with when we do the urinary system in the kidney. This helps to slow the heart rate and increase that contractility. Glucagon has that same effect. Glucagon is like a sugar syrup in your body. Digoxin is a very common prescription medication that you'll see with patients. This increases calcium absorption in the cardiac muscles, so it goes hand in hand with this calcium over here. And then you have catecholamines. Catecholamines are different chemicals your body produces. Some good examples that you'll see pretty commonly are epinephrine. That's part of that fight or flight. It's going to give a really good, strong heartbeat. Or dopamine. Dopamine is that feel-good chemical where you get kind of that flushing, happy feeling because your heartbeat is slowing down, but it's going stronger. Our last part is afterload. Afterload is the amount of resistance the heart must use for pressure to push the blood out. This is an important part of hypertension. With hypertension, the valves open with more pressure than what the blood pressure has. With people who have elevated blood pressure, now it requires even more pressure in that afterload to push blood out. With hypertension, you have a less efficient cardiac muscle to push through because it can't match up with that pressure. This is our whole lab for today. I hope you enjoyed it. If you have any questions or concerns or anything like that, you can send me an email at vswan0001@kctcs.edu. Or you can send a text with any questions on the number found in your syllabus.